Hey, hello everyone. Thanks, Scott, for that great introduction. So yeah, my name's Will Tarpeh. I'm going to talk to you about wastewater and kind of an understudied way that it can play a link between environmental protection and chemical manufacturing from a sustainability standpoint. I'm starting with this picture because this is one of the closest wastewater treatment plants that I grew up near. So you may recognize this. This is formerly Blue Plains. It's now called and been rebranded as DC Water over the past 20 years or so in Washington, DC. And so I grew up just across this river. The Woodrow Wilson Bridge is right there in northern Virginia. But this I could smell from my house several miles away growing up. Last century, I suppose. But now it's really a leader in the field. So I want to talk a little bit about how, broadly speaking, this kind of approach is playing a role today in wastewater treatment and circular manufacturing. So one of the motivations that I like to use for the work my group and I do is that of planetary boundaries, which is probably a familiar concept to many in this room. But in short, we can think about what's the carrying capacity for the globe across different categories. And so we can think about this for climate change and sort of, this is color-coded, and also the larger the radius, the more extreme we are outside of what the planet can handle. And so climate change is one that we're very familiar with, ocean acidification, but we spend our time in this bottom right corner thinking about biogeochemical flows, nitrogen and phosphorus, two of the nutrients that Scott was talking about. And so we think about how can we kind of get the planet back in equilibrium or stasis by achieving a circular nitrogen and a circular phosphorus economy. One of the quotes I like to think about is a pretty old quote from R. Buckminster Fuller, and he's really talking about how we just call pollution something, we call something a pollutant when it's in the wrong place or the wrong time, wrong in quotes here. But the same compounds, nitrogen and phosphorus, that are pollutants in waste streams are actually some of the building blocks of not just biology, but our industrial economy, right? Nitrogen fertilizers feed about half the world, but when they're fertilizers, we call them a product, a commodity chemical. When they're in our water streams, we call them a pollutant. So if we can resituate them, we can start to achieve the circular economy and start to translate some of these technologies. So to focus on nitrogen a little bit, we can think about the nitrogen cycle, broadly speaking. The natural nitrogen cycle is well balanced between dinitrogen, inert nitrogen gas, and reactive nitrogen, kind of all the other forms. Ammonia and nitrate, these first two tend to be in water, and the others tend to be in the atmosphere. So humans, we've done two things to the nitrogen cycle. We've skewed it towards reactive nitrogen, so there's much more reactive nitrogen in the environment. And we've kind of doubled the throughput of nitrogen that goes through the environment. And so the biggest contributors to this are arguably my own field of chemical engineers who invented the Haber-Bosch process. This is, of course, in 21st century, is a real challenge, but it was developed to address, to feed the world, basically. And we need to think about now how to sustain the world. Now, this isn't matched in magnitude by nutrient removal from wastewater treatment plants, and so this is the source of this net linear discharge of nitrogen into the environment. So we see our job in my group as trying to recycle this reactive nitrogen in place so that we're not depending on these energy-intensive ways of cycling nitrogen through this intermediate. So what are the consequences of our existing nitrogen management? Many of you may have seen pictures like this, these algae blooms, these harmful algae blooms. And this is a picture from the Great Lakes outside of Cleveland. And so environmentally, what we're doing is feeding over 100 megatons of nitrogen into the global aquatic ecosystem. And as we make fertilizer, we also expend millions of tons of CO2 as well. Now, from an equity lens, what this means is that Haber-Bosch facilities shown in black here are not, they're not equally distributed around the globe. So that means that if you're in sub-Saharan Africa, most of your fertilizer is coming from one of 4 plants, say, on the continent, or you're paying import charges because the fertilizer has to be transported. So someone in Mali might pay twice as much for the same fertilizer as someone here in the US, even though their income is probably much lower. What this also means is that we're all paying the cost of emissions associated with transport, right? So the fertilizer has to get taken from these fewer than 100 centralized facilities and taken all over the globe. So we're all paying that externality of greenhouse gas emissions associated with transport. So how can we think about this? Maybe not the first thing to many people, but the first thing in my mind is wastewater. How can wastewater play a role here? So one of the ways to think about this is if we look at all the mass of nitrogen that is made via Haber-Bosch nitrogen production, and think about all the nitrogen in wastewater. And for convenience, let's just talk about two types of wastewater: fertilizer runoff, so from agricultural fields, and municipal wastewater, when you flush the toilet and it goes to whatever treatment plant is closest to you, like I showed on the first slide. If you divide kind of that wastewater nitrogen by how much nitrogen we use, you get around 30%. So that's kind of our envelope of what we could address by capturing nitrogen from wastewater, around 30% of fertilizer production. Now, you could also think about what form of nitrogen should we focus on. I talked about ammonia and nitrate. And so you might say, should I focus on ammonia, should I focus on nitrate? And my answer to that is both, or yes, because they have similar mass magnitudes in terms of what's available in the environment. So whether you want to take nitrate and turn it into something valuable, or take ammonia and turn it into something valuable, both are potentially profitable endeavors. So one of the things we try to think about is wastewater is this huge category. Most of us think of wastewater as what happens at the municipal wastewater treatment plant, or you might just think about your toilet at home. But there's so many different types of wastewater that we can kind of represent as these different pie charts. And I'll suffice it to say that there are at least 4 facts that are important about a given wastewater. And remember, each wastewater here is one of these pies. So we can think about its global flow rate, how much of that wastewater there is, how many dissolved solids are in it on the y-axis, where the global flow rate was on the x-axis. We can think about the size of these pies, so to speak. That's the dollar value of what's present in that wastewater. So the bigger the pie, the bigger the monetary opportunity. And then we can think about all the different elements that are in it. So a lot of times when we think about wastewater, the first thing that comes to mind that you can recover is water, drinkable water. And of course, that's true. And there's much more on the table in wastewater besides just the water, right? And so that's what we're trying to drive home here. There's plenty of commodity chemicals that we can manufacture from wastewater. So just thinking about nitrogen, some of the ways that we can think about modulating what's happening here, we can think about changing oxidation states between nitrate and ammonia, changing the physical state. Are we doing a solid, a liquid, a gas? Changing the chemical formulation, and also changing the product purity. So the ways that we think about this are trying to develop refineries, and we sort of take back that term from oil and gas on purpose here, but in a way that we're saying refining means taking a raw stream like wastewater, or oil and gas would say like crude oil, and then being able to produce dozens of products from it on site, right? And tailor these different processes to make, frankly, whatever we want. And so we're using electricity here because it can be flexible scale, it's easily integrated with renewable energy, think photovoltaics on site. We can achieve process control, and maybe most importantly, we can replace chemical inputs with electricity. So instead of trucking acid and base all over the world, we can produce acid and base on site just using renewable electricity. And that's what we're after here in terms of point-of-generation wastewater and delivering commodity chemicals where they're needed. And so again, these are some different forms of nitrogen that we can use and do these reactions to make different forms anywhere you want to stop along this oxidation state ladder. So in terms of what my group does, we can divide it into kind of 3 areas. These electrochemical processes that I described, these selective materials that might help us get just one element out of wastewater. So nitrogen is the focus today, but you can also think about something like lithium-ion battery recycling, where we want to get just the lithium out of batteries that we're trying to recycle so that we can make new batteries. But that's a kind of a needle in a haystack problem, and that's what we're after. And then a large part of the group is also focused on actually translating some of these results out into the world and trying to design actual technologies that people can use. So I'll give you just a kind of quick insight into a couple of these. So from the electrochemistry standpoint, one of the core things we do is use charge and volatility, which are 2 properties of nitrogen, to separate it selectively from really any wastewater that contains nitrogen. So how we do that is we basically hook up 2 different electrodes, metallic electrodes, and some ammonium-rich wastewater comes in. We have salt and acid in these other chambers, and so this is a reactor that you can hold in your hands. And so we're doing a reaction here, oxygen evolution, where we're acidifying this, the wastewater that comes in. And so ammonium becomes our major version, NH4+. That is charged, of course, and can be attracted to that negative electrode, cross a selective membrane, and at that negative electrode, will basify, increase the pH, and turn that ammonium into ammonia, simply by deprotonating it. So here we've separated ammonia based on charge, just a positively charged species. That's not enough because, as you can imagine, there are other positively charged species in wastewater, sodium, potassium ions, et cetera. So we need another selectivity filter here. And what we use is the fact that we can make ammonia into a gas. So now we select for the fact that we happen to make a gas by increasing pH. And then we can capture that gas across a membrane that doesn't let liquid through but does let gas through. So what we've done is separate ammonia on its own by virtue of its charge and volatility. So what does this look like in practice? It means that this is treating real hydrolyzed urine. This means that we can turn all of the nitrogen that was in the anode feed chamber into nitrogen that's in the trap chamber. I said we could do this for multiple wastewaters. What I mean by that is that we designed this for real urine, but we can take any really ammonia-rich wastewater and do this at high efficiency. And these efficiencies are how much ammonia you get in the product versus how much was in the feed wastewater. So as you can imagine, there's a lot of engineering that has to happen to be able to do this for all these different wastewaters. And so, like I said, we're trying to translate this out of lab. And so several of my students, Anna and Kindle in particular, and this is in partnership with the Sustainability Accelerator, are trying to do long-term testing, so run these techniques for months rather than just days, the data I just showed you. We're doing some collaborative work with practitioners in both Senegal and Kenya with a focus on decreasing the cost of sanitation of toilet access by providing value from them. And then, of course, we're partnering with the Kodaga Resource Recovery Center here on campus to try to get out of the lab at something like 10 liters a day to something more like 30,000 liters a day, which is a fun chemical engineering scaling problem, but one that we're hoping we're up to and trying to understand some of the really practical challenges, like how long do your membranes and electrodes last and these things like that. So another application of this work also is miniaturizing, rather than making it bigger, miniaturizing these to actually make small-scale sensors to sense nutrients as they go throughout the environment. And so this is collaborative work with Kate Maher and Debbie Sineski. But you can imagine, and we've 3D printed a smaller version of this, so this part could fit in like a few of my fingers. And so the idea here is that we can combine the selectivity of the approach I just showed you with the sensitivity of some different electrodes that Debbie has developed and make deployable sensors that really sit in fresh waters, for example, or coastal waters, and tell us when there's a plume of nitrogen coming so that we can attempt to remediate it. So kind of at the last thing I wanted to do is just give you a little thought about how we design these electrochemical separations as well. And so in short, the main things that we think about when we try to design an adsorbent, and you can just think about this as like the inside of a Brita filter, but selective, right? So rather than just removing all the contaminants from your drinking water, we want to get just one out at a time. So you might think about the capacity, how much of the pollutant you can get out, the selectivity, which pollutant you can get versus another, and then the regenerability. And so what we've done here at a molecular scale is introduce a modification here where we put metals onto a resin, and that allows ammonia to be selectively recovered. Just for time's sake, I'll show you on this x-axis are several different adsorbents in terms of and on the y-axis is their ammonia selectivity versus potassium, a common competing ion. And in fact, one that's so similar to ammonium that it's really hard to separate them. So you can imagine these nitrogen selective adsorbents as anything with a value greater than 1 here. And so before we developed these, we screened kind of far and wide. I could put hundreds of different adsorbents here, but we couldn't find one that was actually intrinsically ammonia selective. And so by adding these metals and actually adsorbing ammonia NH3 rather than ammonium NH4+, we were able to get this an order of magnitude higher and achieve a selective nitrogen material for one of the first times. So I'll end with just a few of the other aspects of what's going on so that you don't just think I only think about nitrogen, although I do spend a lot of time thinking about nitrogen. Some of the other things we do are looking at producing actual valuable chemicals from desalination brine, which I consider a wastewater of wastewater, so to speak. So kind of a dirty secret of desalination is that you often produce almost as much or as much salty water as you do clean water, and we need to do something with that salty water. If you're near the ocean, ostensibly, people are okay with discharging it. But if you're inland, that makes reverse osmosis it makes desalination a non-starter. Also thinking about phosphorus recovery, I mentioned lithium recovery from spent batteries and some biological work on nitrogen selective membranes. So with that, I'd love to take your questions and thank my group, and happy to discuss more.